So we went out and built, we were testing this, and we went out and built the world's most sophisticated ship simulator. So we can take thousands of ships, disperse them inside a theoretical field of view, and we simulate every physical aspect we could think of: the roll and pitch of the sea state, the transmit power of the radio, the alignment of the antenna, Faraday rotation in the antenna, atmosphere, everything we could think of. And we can create an RF signal that's the conglomerate of all of that. And then we can use that to develop the decolliding technology. And as part of that exercise, we went and bought a bunch of these commercial receivers. And it turns out the very best ones perform better than the theoretical studies that came out. And that's what this thick blue line is. And so this area, why is it better than theoretical? And the reason is that in space there's a lot of Doppler shifting going on, and a number of other things that come in. And it turns out the really good ones are close to this line, but the cheap ones that don't work very well, that aren't tuned properly, actually perform better in a space environment. But still, the fundamental problem is that you might have, say, 3,000 to 7,000 ships in the busiest areas of the ocean. Nobody knows for sure because nobody's ever had this data before, but we did a big survey and we studied this a lot, and most people would agree that in the North Atlantic, the Gulf of Mexico, the Straits of Malacca, there's a number of areas where the most interesting parts of the world, where there might be 4,000 or 6,000 ships inside that field of view, and that's the problem you have to solve. The other thing we did was about 10 different, over 3 years, we've done more than 10 market research studies. And one of the questions we asked the maritime authorities was, how well do your terrestrial systems work? If you're measuring this, you put a base station out, it's supposed to cover 40 miles out. Of all the ships that come and go to your port, how many of them do you detect with this system in real time? And the average answer was 78%. So terrestrial systems do a probability of detection over the full area of interest of about 78%. So that's our target. So we ran all of this and put it all through our decolliding technology, and we get this curve. And we're very, very happy with this, as you can imagine, because in the busiest areas of the world, we're performing pretty darn close to the performance of the terrestrial network. And we have a very nice fall off here, which allows us, in a dynamic situation, to perform even better, because quite often there'll be a busy area, say the North Atlantic. As you come into that area, you don't have 5,000 vessels in the field of view. So you do very well at the beginning. Then you get 5,000 in the field of view, and it may drop off to 75 or 80%. Then as you leave, you get them again. So this gives us a superb performance capability. There are only a couple other players in the market doing something like this, and they're both using standard receivers. So you can see we have a huge competitive advantage in doing this. And for the first time, not only do we do a lot better than our competitors, but we actually meet the needs of the market. And that's really the key to all of this. And that gives us the tagline of every ship, every time. So to do this, does this actually work? So we ran a whole bunch of trials on what I showed you before were simulations. And 2 years ago, our second anniversary is coming up, we took this satellite, which we built with the University of Toronto, and attached it to an Indian launcher and sent it up on a rocket. It had a design life of 60 days, and the purpose was to collect enough data that we could prove that our decolliding technology worked. However, it works so well that it's still in operation today. It's coming up on its second anniversary. And in fact, we just finished a project for Canadian Department of National Defense to help with the security for the Olympics off the west coast of Canada. So every day we were taking snapshots off the west coast of Canada and identifying every ship in Canadian waters using this particular satellite. And so this has been an extremely successful bird for us. So, how well is the real world compared to our simulations is the question. So because the way the system works, we collect the spectrum data. We do a little bit of work on the satellite, but in this system we also bring the spectrum data down, digitize spectrum down, and we process it on the ground. Because we have the spectrum, we can run it through a standard receiver, and this is what you see here. So in a 90-second snapshot, it's only 90 seconds of data over the Atlantic, we get this kind of data. And when we run it through our decollider, we get that. Again, we're really happy with the results of this. Both of these exactly the same data set, and it works pretty well when you say, you know, this is us and this is our competitor. Which one would you like to buy? So the conclusion is it works. And what you see here is less than 2 hours of total observation time. It's a montage of 90-second snapshots over 8 or 9 months. And this is the first truly global ship density distribution ever produced. At least it's not in the black world of some of the militaries. And so it's really easy to see the shipping lanes here, lots of activity in the Persian Gulf. And this maps reasonably well to the predictions that were done by Amber and others that do this kind of stuff. But we're really happy because every dot on there is real data. So this is a little bit of a movie that'll show you how this. There we go. So this is all real data collected. This up here is the terrestrial line of AIS base stations in Nova Scotia. And as we go around the world, we're able to get all of the data from these vessels. Nobody's ever been able to do this. Certainly not up in the Arctic like this. You know, we thought that might have been an error point, but it wasn't. It actually was a Canadian icebreaker up there. And what we do is we fuse this data together with other people's databases to pull up some of these pictures. So this is the DriftNet area. Here's you ever watch that dangerous fishing fleets on the Discovery Channel? That's these guys up here in little clusters. This is off of India. So this is Mumbai. They're very worried about ships coming in there because of the terrorist attack. It's really interesting. There's no ships that are sailing really close to the shore off of Somalia. Norway's particularly interesting. Imagine if you had to put a base station inside every one of the little fjords inside Norway. It can be a real problem there. So this capability is brand new, and that's all just with 90-second snapshots. Sorry? Animate it in what sense?
You track the movement of individual ships in a 24-hour period.
Well, I'll show you how the system works, and we would certainly be able to do that out of the database, but the system has some limited capability in terms of how often you get to it. You'll see that in just a second. So, having proven the technology, how do we turn this into a business, and what are we doing? So this is the global view, and the key here is that you want to cover that whole planet. So I'm going to show you the animation here, but the key quality parameters, once you get the detection rate up high enough, which is what we have, every time you fly over the ship, you want to pick it up every ship every time, but you also want to go over that ship fairly frequency. Then you have downlink latency, which I'll show you, which is how long it takes the satellite, once it picks up the ship, before you can get it off the satellite and down to the ground. And then the network latency, which is how fast can you process the data and move it around the planet and get it on a screen for a customer. So let me play this. So what you see here is this is a typical field of view, and you'll pick up a data, say here, and the Earth is rotating underneath the satellites. So this satellite on this orbit picked this stuff up, but the next time around it's going to miss some of those. And so you need another satellite over here to be able to get at the next orbit. This is really hard to describe without a 3D picture, and I know everybody in this room understands the value of 3D movies, but this is pretty valuable. So with this 6 satellite constellation and this wide field of view, we can pass over every point on the planet about every 90 minutes. And you can see that it's latitude dependent because one satellite goes over the North Pole every 90 minutes, but it only goes over the equator once every 12 hours if they're in true polar orbits. Now getting the satellites to actually behave in these nice, beautiful orbits is not as easy as you might think, But nevertheless, that's the basic plan and the quality level that we will provide.